Welcome back to Beyond the Comfort Zone Talking Shit with King-KAMBUF.
Great to be here.
Today we are doing a really high-intensity session. This is a truly specialized deep dive into some material that was generated for a, let's call it an elite multidisciplinary designer.
Yeah, this isn't your standard stuff. We're talking about a document that pulls from architecture, high-end engineering, urban planning, even public governance.
Exactly. And the source we're digging into today is called Architectural Insights with King-KAMBUF, Friday, November 28, 2025. It's from the services of King-KAMBUF PS Architecture's daily mentorship digest.
Right. And just to set the stage, we're jumping straight into what are basically PhD-level concepts here. The whole philosophical shift we're looking at is moving away from designing a static object.
Like a building's just a rock you place somewhere.
Exactly. And moving towards a structure that has, and this is the key phrase, adaptive structural intelligence.
So the mission today isn't just to, review these concepts, but to really get the implications. We need to go way beyond just gravity and wind loads.
Oh, way beyond.
We're confronting forces that are often just completely ignored in standard calculations. Things like microvibrations, latent hydrologic loads, temporal shifts, things that affect materials over years, not just in a single moment.
And this material, it forces us to see architecture not as some finished inert block of concrete and steel, but as a living sensing system.
A living system, I like that.
Yeah, the structure is in a constant dialogue with its environment. So our job today is to walk you through how these sources detail structures adapting to these dynamic, often conflicting, and totally invisible pressures. We're talking thermal, hydrologic, vibratory, and atmospheric forces.
Okay, let's unpack this. Let's start with the most visible part of this adaptation.
Yeah.
The literal skin of the building. We're talking about the active building envelope.
Right. The adaptive materials and kinetic systems that can actually turn environmental hazards into structural mechanisms.
And we're starting in probably the most hostile environments you can imagine. The Arctic. The idea here feels revolutionary, treating extreme cold not just as something you insulate against.
Not as a passive force, no.
But as a structural ally, something to be harnessed.
Exactly. This is the focus of a concept called polar responsive structural coatings for extreme latitude facilities. The research, a lot of it coming out of places like Tromsø and Alaska, right near the Arctic Circle, it centers on these polymer ceramic coatings.
Okay, so what's so special about them?
Well, the crucial property is rheological. The stiffness of these coatings, it doesn't just stay the same. It actually increases, and significantly, as the temperatures just plunge into those negative double digits.
Wait, hold on. Increases. That feels totally counterintuitive. Aren't engineers trained to fear the cold?
They are.
Materials get brittle, fracture risk goes up because of thermal contraction stress. Why would increasing stiffness be a good thing?
It's all about load management in a super high-stress environment.
Yeah.
So picture a research facility or maybe a resource plant up in the Arctic.
All right.
It's facing these colossal persistent wind loads, probably some seismic activity, and the dynamic load of ice just building up on it. So if the outermost layer, that primary structural coating, becomes more rigid, more resistant, precisely when the wind and the ice are at their absolute maximum, it just drastically enhances the structure's adaptive load resistance.
So instead of just pouring in tons of passive insulation and relying on internal heat to keep the material stable, you're engineering a skin that gets dynamically tougher when the environment is at its worst.
You got it. The source material explicitly says this fundamentally changes the design equation for structural performance in these cryogenic environments. Cold is not just mitigated, it is actively utilized.
But there has to be a trade-off, right?
Of course. And the sources do touch on this. What happens when the temperature rises rapidly? You get a sudden Chinook wind event, and that coating has to rapidly relax its stiffness.
Are you introducing a new failure point, like delamination or something?
That's the question. Or maybe micro-fatigue during that temperature transition. The reliance shifts from just thermal insulation to the long-term integrity of the material science itself.
That's a serious deep dive into material science. Okay, let's pivot completely from the frozen north to the chaotic density of a global megacity.
And the flow of human energy?
Yes, managing pedestrian turbulence.
This is a spectacular example of architecture becoming truly dynamic, responsive, and frankly, a little bit manipulative. The concept is kinetic pedestrian flow floors.
Okay.
They're being piloted right now in these super high-density metro interchange hubs. Think Seoul, Shanghai.
When I think of those hubs, I just picture that terrifying moment where thousands of people from different trains pour onto one platform at the same time. It's not a crowd, it's a physical pressure wave.
That pressure wave is exactly what they're trying to manage. It creates turbulence, friction, dangerous congestion hotspots.
So what's the solution?
The architectural solution is to embed these sub-mechanized plates into the floor system. Now, these aren't turnstiles or gates or anything obvious. They subtly shift. Milliseconds in one direction, then another, guided by what the source calls kinetic scripts. They're sensing real-time density and just regulating the flow.
So the floor is actively, but subtly, controlling how fast and where people move. It's basically preventing that human energy from turning into a destructive bottleneck.
Precisely. Transit flow becomes a dynamic architectural mechanism. By anticipating and regulating that turbulence, the system optimizes movement. It's a very calculated, very subtle architectural action.
But that raises a huge governance question, doesn't it? If the architecture is invisibly steering people based on some predictive algorithm, the kinetic script, does the city suddenly take on new liability?
Oh, for sure.
What if the script fails? Or worse, guides people into an unexpected pressure point and someone gets hurt?
That's the crux of it. This absolutely requires a merging of, system safety engineering and public liability policy. It's a whole new frontier.
A powerful ethical and legal point that has to be in the design brief from day one. Sticking with fluid dynamics, let's move from people to water.
Specifically, roofs that have hydrologic memory.
And temporal devices. What does that even mean?
This moves our focus to urban hydrology sustainability. A lot of this research is coming out of the Netherlands. The concept is called heat gradient rainwater memory roofs.
Okay.
These roofs have phase change layers built into them, so materials that absorb or release huge amounts of heat when they change state, like melting or solidifying.
And how does messing with the thermal state help you manage rainwater?
So the layers remember the heat gradients over time. This thermal history is then used to actively optimize how much rainwater you capture during seasonal evaporation spikes.
Okay, break that down for me.
In Northern Europe, or really any place with hot, dry summers, you have this problem.
Okay.
The hotter it gets, the faster water evaporates.
Right, which messes with your drainage or your water storage.
Exactly. It destabilizes the volume you think you're collecting.
Okay, I think I'm getting it. So if the roof has absorbed a ton of heat over a hot, dry period when a sudden storm hits, those phase change layers can then modulate the temperature of the water or the substrate.
Yes.
And minimize how much is lost to evaporation, meaning more of it actually gets to the collection system.
You've got it. It's designing for time, not just for an instantaneous load. The roof effectively becomes a temporal hydrologic device.
Right.
It stabilizes the runoff volume precisely when the environment, those peak evaporation months, would normally destabilize it.
It ensures the infrastructure gets the water it was designed for.
It decouples the collection rate from short-term atmospheric volatility. It's brilliant.
From rain memory to intense heat management. Let's jump to the UAE and research into aero-tuned shade membranes for what they call heat pulse urbanism.
This is such an elegant solution. It's for those rapid, really intense thermal swings you get in desert regions. So instead of using energy-guzzling mechanical louvers...
Right, with motors and gears and all that.
These are membranes that automatically inflate or contract based on thermal pulses.
Thermal pulses.
Yeah, think rapid, short spikes in temperature, like when the sun breaks through fast-moving clouds for just a minute.
So the heat itself is the mechanism. The sudden pressure difference from that heat pulse makes the air inside the membrane expand or contract, and that adjusts the shading.
Correct. The core benefit is huge. Heat management becomes aerodynamic instead of mechanical. That dramatically cuts down on maintenance and system complexity.
But the engineering challenge sounds significant.
It is. You have to design the whole facade geometry to stay stable during those rapid transitions. I mean, when that membrane inflates instantly, the structural tension changes dramatically.
You could get oscillation or flow.
Or even material fatigue failure right where the membrane connects to the frame. The design has to handle that dynamic stability under a sudden pressure shift. It's a huge challenge.
It's just incredible. We're designing skins that literally breathe and regulate themselves based on these microclimatic shifts. Okay, so if we move from that macro level, from human and environmental forces to the invisible forces happening within the structure itself, that gets us to part two.
The nonlinear conflicts.
Right. This is where we go deep into those unseen interactions. Thermal, hydrostatic, vibrational. that often gets simplified or just missed in standard engineering. We're starting below grade.
Subsurface duality and thermal stress.
Below grade mechanical vaults, subway tunnels, basements. These are ground zero for this invisible conflict.
And we have to model what the sources are calling the thermal hydro expansion conflict.
That sounds incredibly complicated. You're dealing with forces that are peaking and troughing on completely different schedules.
That is the core issue, and it's why the interaction is nonlinear. So as the seasons change, the soil and rock around these deep vault walls, they expand thermally, they push inward.
Okay, that makes sense.
But at the same time, or maybe a bit later, the hydrostatic pressure, the weight of the groundwater is also changing, and it's also pushing on those walls.
So you have two massive cyclical forces acting on the same wall. If they peak one after the other, that's bad. If you peak at the same time,
Catastrophic.
yeah.
And they interact non-linearly. So if the thermal expansion of saturated soil is happening while the hydrostatic pressure is also rising, the effective stress on a joint is way, way greater than just adding the two loads together separately.
So the whole is greater than the sum of its parts, in a bad way.
In a very bad way. The sources really stress this. Subsurface zones are dual force systems. Temperature and water loads amplify each other, and they put severe stress on joints and connections.
So with that complexity, how reliable are the current nonlinear modeling tools? I mean, are engineers relying too much on software and maybe not enough on just good old physical redundancy here?
That is the critical challenge that this KING-KAMBUF material poses. The models need to incorporate phase shift, the temperature dependency of soil mechanics. Standard finite element analysis really struggles with this.
So what's the strategy?
The best strategy, it suggests, is rigorous physical testing of the joint materials under simulated nonlinear compounding stress, moving toward robust redundancy rather than pretending you have absolute predictive certainty.
Here's where it gets really interesting. I always pictured a steel anchor as, just a rigid thing. To think of it as a torsion amplifier that's visualizing force in a totally new way. Let's talk about the torsion amplifiers.
This is so vital for any composite mid-rise construction, especially where the facade geometry introduces asymmetry.
Like cantilevered balconies that are just sort of scattered irregularly along the building face.
Exactly that. So you have a concrete slab connected to a steel frame. That's your composite action. Now, if one side has these massive balconies and the other side has none, how does that translate into amplified torsion?
I'm picturing it now. The uneven load distribution creates the severe eccentricity, right, relative to the building's center of rigidity.
That's it. So when forces act on that slab, let's say wind, the difference in load path and rigidity introduces a rotational movement, a twisting.
And that twisting energy has to go somewhere.
It has to be resolved where the slab meets the main structure. And that anchorage point, the one holding that irregular cantilever, it doesn't just resist shear and moment anymore, it becomes a literal torsion amplifier. It converts that asymmetrical load into a massive rotational force right at the connection.
And the solution mentioned is torsional anchorage offset analysis.
Yeah.
So for the listener, what does that actually mean in practical terms?
It's an analysis to precisely calculate the rotational displacement under that asymmetrical force. You're calculating the anchor's requirement not just to hold the weight up, but to stop the slab from trying to twist the main column it's attached to.
Like the torque on a wrench.
Exactly like the torque on a wrench. If your resistance point is offset even slightly from the line of force, the rotational component just spikes dramatically. You often have to significantly reinforce or even relocate anchors to handle that amplified twisting energy.
And this isn't just in balconies. We see similar issues in parking structures.
Yes. Modeling torsion-induced ramp asymmetry. A parking ramp is basically a giant structural helix, right?
Right.
It creates these continuous off-axis lateral forces as cars move up and down. But the critical moment is during a dynamic event, like a seismic load.
The ramps would redistribute that energy all wrong.
Irregularly, yeah.
Yeah.
They create these stiffness mismatches between the inclined ramp and the flat decks next to them. This leads to severe torsional hotspots, and it just warps the whole lateral drift pattern of the structure.
So if the building starts shaking, the ramps act like a giant asymmetrical lever, twisting the entire floor plate unless you specifically analyze for that.
Exactly. If you ignore that torsional effect, you are leaving major seismic vulnerabilities on the table.
Okay, now let's talk about the structure as receiver. Vibrational rhythms. The idea that rotational equipment sets a beat that the building has to resist.
Yeah, and the specific example is wastewater pump galleries.
So in a pump gallery, you've got these high-powered impellers running constantly.
And they establish these periodic structural rhythms, a constant beat. The critical design failure, which the sources highlight, happens when the equipment's operating frequency, its rotations per minute, synchronizes with the natural vibration modes of the floor slab.
For our multidisciplinary listeners, what exactly is a natural vibration mode?
Okay, think of it this way. Everything has a natural frequency, like a guitar string. You pluck it, it vibrates at a specific pitch.
Okay.
A concrete floor slab, when you apply force to it, also has specific frequencies it prefers to vibrate at. If the rotational rhythm of the pump, the impeller harmonic, matches that slab frequency, you get resonance.
The tuning fork effect.
The tuning fork effect.
Yeah.
And that causes massive amplified structural deflection. You get excessive micro-cracking, slab fatigue. It's especially bad at those vulnerable slab-to-column connections.
So the design has to include impeller harmonic frequency separation. You engineer it so the machine frequencies and the floor's resonant modes are kept completely separate.
It is absolutely essential. The building has to be, deaf to the beat of its own mechanical systems.
And there's a second example, right? On manufacturing floors with robotic arms.
Yeah, analyzing eccentric operational load bursts.
A robotic arm moves a heavy payload, fast and precise.
And when that arm accelerates rapidly, it introduces a centrifugal burst. Since the load is eccentric, it's way out at the end of the arm, not at the center of the slab. That burst creates a micro-torsion on the adjacent slab sections.
It's a tiny little twist over and over again.
A tiny twist, but over time, that repetitive micro-torsion, even if it's small, can couple with the slab's frequency. This leads to fatigue and potential localized structural failure right in the areas supporting that expensive equipment.
Wow. So sources stress the need for, rigorous vibration zoning and risk analysis on those floors?
Exactly.
Okay, now let's move to a really brutal repetitive force. High-frequency shock in freight architecture.
This scenario is it's devastating. It involves crack pulse propagation in precast panels right next to 247 heavy-duty truck lanes at an intermodal freight hub.
The numbers are staggering. We're talking 600 to 900 shock pulses per day.
Let's put that in perspective for you. 900 pulses a day, 365 days a year. That's nearly 250,000 kinetic shock events annually. It is just relentless.
And it's compounded by a huge daily temperature swing, sometimes 10 to 34 degrees Celsius, so the structure is constantly expanding, contracting, and getting hammered.
And the data presented is just stark. A crack propagation rate of up to 1.1 millimeters per week. That rapid degradation shows that these vehicular pulses, they act like low-level, high-frequency microseismic events.
So it's not enough to design the wall for the static weight of the truck.
No, not even close. You have to design for continuous kinetic energy absorption.
So what was the solution workflow the engineers came up with?
It was all about isolating that kinetic energy. First, they had to rigorously identify the precise vibration signatures of the truck impacts. Second, they used elastomeric vibration isolators, basically thick rubberized pads behind the precast panel clips.
So a cushion.
A very sophisticated cushion. And third, they reinforced the panel joints with specialized pulse absorption plates. Freight architecture requires sophisticated, repetitive loading wave absorption. You have to treat that kinetic energy as a quantifiable, destructive force.
Okay, we've covered thermal, hydrologic, vibratory forces. Let's wrap this section with the last invisible element, the atmosphere itself, atmospheric margins and microclimate effects.
And we have 3 really remarkable examples of how air movement and moisture actually behave structurally.
The first one is in cultural museums with these huge, tall atria. Designers have to assess microhumidity plume drift. Why does height create humidity plumes?
It's because of the thermal stack effect, that chimney-like force you get when warm, less dense air rises rapidly in a tall space. The air movement is vertical, and if the air is humid, that creates a rising column or a plume of moisture. So if you have sensitive materials, artworks, archives at different vertical levels, those plumes can distort the relative humidity zones.
So the RH levels at the top could be way too high or too volatile for the art up there.
Precisely. Humidity gradients start to behave like these invisible structural zones that can degrade priceless assets.
The second one, high-rise winter gardens modeling thermal arch lift.
This is an incredibly subtle physical phenomenon. The warm interior air in a big, sealed space like that creates these upward lift pockets, positive pressure, right up against the ceiling or the roof of the enclosure.
So the warm air is literally trying to lift the roof of the garden.
In a micro way, yes, it's microthermal lift. But over years, this consistent, subtle distortion can strain seals, lead to premature stress fractures in the glass, and warp the entire curtain wall geometry. It has to be accounted for in the structural detailing.
And finally, the idea that latent moisture load is a structural mass.
Ooh.
Latent load shear drift in high humidity sports complexes.
In huge spaces like indoor aquatic centers, the sheer mass of water vapor in the air, the latent moisture load, is enormous.
We're talking tons of water just floating.
We are. And that moisture adds mass to the building's total volume. The research suggests this added mass subtly shifts the building's lateral drift patterns. So when the building is hit with high lateral forces wind, seismic activity, its structural response actually changes based on the density of the air inside it.
So humidity isn't just about comfort. It's a critical mass load that changes how the building moves.
That's the takeaway. It has to be factored into the structure's response to lateral movement.
That is taking physics to the absolute extreme.
Yeah.
We are now seeing the environment as a set of forces that constantly apply, subtract, and multiply structural loads. Moving into part 3, we're looking at truly extreme design scenarios, the integrity of load paths during temporary states, and how architecture is now merging with public governance. It's a shift from isolated engineering to system strategy.
We start at extreme altitude. A high-altitude autonomous research station that was experiencing panel buckling because of rapid atmospheric pressure cycles.
A day-to-night atmospheric shift causing an 8 to 12% pressure drop. That is a massive pressure swing on the facade.
Yeah, high-altitude architecture operates right at the atmospheric margins. The rigid panels they were using were buckling because the internal and external pressures just couldn't equalize fast enough across that rigid core material.
So the pressure difference itself was acting as a primary structural load.
A violent one, trying to push the panel inward or outward.
So the solution wasn't just to add more stiffness or thicker panels. It was to let it breathe.
Exactly. It was totally counterintuitive. They replaced the rigid cores with flexible microcell structures and added pressure equalization grooves at the vertical seams.
So the panels can vent and equalize pressure without building up that stress.
Right. And the lesson here is so clear for anyone designing in extreme conditions. You have to treat atmospheric pressure as an active, fluctuating structural load, not just some static background condition.
Okay, next, we're back to water, with terraced hillside campuses and hydrocascading failure.
This is a lesson in hydrodynamic momentum. On a steep slope, rainwater accelerates as it goes downslope. It gains energy. So if the drainage system on the highest terrace fails or overflows,
that water hits the second terrace with way more velocity and volume than it was designed for.
It's a literal domino effect of water.
A cascade.
Exactly. That sequential accelerated overloading can lead to timing failure, where the terrace walls fail one after another in rapid succession because each wall is getting hit by the failure of the one right above it.
So you can't just design each terrace in isolation.
No. You need cut-slope reinforcement and a meticulous analysis of the speed and volume of water transfer between the terraces.
This concept of architecture servicing a greater urban system, this is taken to a whole new level with the idea of vertical aquifer towers for drought-risk cities.
This is fascinating. Cities facing chronic water scarcity, the paper mentions Cape Town, Mexico City, are exploring these hybrid groundwater recharge stacks that are integrated directly into mid-rise structures.
So the building isn't just sitting on the ground, it's actively participating in stabilizing the water table below it.
Precisely. The building is designed to channel and filter rainwater and runoff deep underground to stabilize declining aquifers. Architecture literally becomes an urban hydrologic organ.
Structural and governance challenges must be immense.
Oh, huge. Structurally, you have to balance efficiency with creating these multi-layer recharge basins that handle massive amounts of water infiltration without compromising the building's own foundation or, increasing geotechnical liability for the whole block.
And what about the policy side? The regulatory insights. I mean, who owns the water being recharged? How does this affect municipal water rights?
And this is where architecture slams right into public governance. When a private structure performs a public service like recharging a shared aquifer, it introduces massive legal complexity.
Does the building owner get a water credit or something?
Does the municipality share liability if the foundation starts to shift? The briefing suggests these towers require a whole new class of municipal engineering guides that treat the structure as part of the public utility infrastructure, not just a private asset.
Wow. So the structure becomes a political and legal entity as much as a physical one. Okay, let's move on to designing for construction and rearrangement load path integrity in temporary states. This is crucial for things like modular student housing.
And evaluating what they call load jump discontinuity.
Right.
Modular housing is inherently dynamic, right? It's designed to be lifted, disassembled, reconfigured. But that period during the crane placement, when a module is being transferred from the sling to the columns below it, that's a highly critical moment. The load path shifts instantaneously, a moment of load jump discontinuity.
That's a huge short-duration stress spike that a designer might completely overlook if they only model the final static building.
Correct. Moving these units alters load paths temporally, and it introduces dynamic impact loads. The KING-KAMBUF material just hammers this point home. Temporary states, construction, rearrangement, even deconstruction are critical load design phases.
And if the connection plates aren't designed for that high-impact stress, they fail.
They suffer premature failure or fatigue. And we see a similar issue with modular bridge systems.
Right, testing span junction stress reversal
Yeah.
from directional traffic waves.
A modular bridge is a series of joined segments. When a wave of heavy trucks moves across it, say in heavy one-way traffic, the stress patterns at the joint plates can briefly reverse from compression to tension or vice versa.
Especially if the joints are a bit fatigued or misaligned.
Exactly. And this repeated stress reversal, the bridge being briefly pulled apart and then pushed back together, causes junction fatigue. It requires specialized joint plate optimization to withstand millions of cycles of reversal without compromising the whole span's integrity.
Now we shift to architecture as diplomacy and policy. The RFP for the Northern Straits Maritime Governance Center. This is binational, spanning Victoria, BC, and the Puget Sound region.
This is a profound convergence of geopolitics, ecology, and engineering. It's designed as a binational center for maritime ecology, shipping diplomacy, and critical tribal federal coordination. The architecture itself has to facilitate these complex, often sensitive negotiations between sovereign nations and indigenous communities.
How does the briefing frame the building philosophically? What's the big idea?
The recommended thematic angle is to frame the building as a civic marine oracle. Yeah. The architecture must actively reveal cross-border maritime behavior and serve as an environmental treaty platform. And this is achieved by integrating the coastal engineering data currents, wave action, ecological sampling directly into the building's functional and aesthetic systems.
So the building is meant to unify all these different stakeholders, tribes, cities, provinces, federal agencies, under a shared stewardship by making the environment they all share visible.
Absolutely. And this requires a spatial design that can support the highest level of policy negotiations, which have to be private and secure, while simultaneously integrating public access, eco-modeling labs, and these cross-border negotiation halls all seamlessly.
And the structural challenge is the marine environment itself.
Resisting coastal erosion, high tides, while staying visually and functionally transparent about its purpose, a huge challenge.
This shift into architectural diplomacy leads us right into the idea of theatricalizing dynamics, design prompts that make these invisible forces visible and experiential.
The first prompt is just amazing. It's the diurnal gravity theater. The challenge is to design a performance center whose spatial geometry subtly shifts in response to solar-driven temperature differences.
So it dramatizes the Earth's daily thermal cycle.
It literally acts it out.
That is a stunning concept, but it requires some extraordinary material science. How can the movement be passive and still create a functional acoustic space?
Well, the movement has to be passive, right? Driven entirely by the thermal expansion and contraction of materials. You're probably looking at bimetallic strips or shape memory alloys integrated right into the load-bearing or cladding systems.
And the acoustic constraint is the hardest part.
By far. As the volume of the space changes, the ceiling subtly arches, the walls slightly angle, the reverberation time and the acoustic focus just shift all over the place. You'd need some kind of adaptive acoustic treatment that maintains functional quality across all states of that thermal cycle. It's a monumental exercise in using material behavior as architectural expression.
And the second prompt, the Maritime Civics Lantern, this ties back to that governance center.
Right. Here, the governance chamber translates real-time maritime data currents, tides, shipping density into spatial and lighting behavior.
So like kinetic louvers or gradient glass that changes its opacity or color based on a live data feed from the streets.
Exactly. So if a major container ship enters the straits, the lighting in the room subtly shifts color, or a wall segment slowly rotates. The policymakers are literally immersed in the data they are discussing.
It connects them physically to the consequences of their policy decisions.
It does, and the briefing is very specific. The movement must be data-driven, but critically non-distracting for high-level negotiations. It has to be peripheral, almost subconscious. It reinforces the building's role as that civic oracle without getting in the way of the actual work.
It's a fine line between dynamic architecture and functional neutrality.
A very fine line.
Okay, part 4. We've established that every force, thermal, kinetic, hydrologic, influences the structure. We need to synthesize this by looking at the interconnectedness of stability and life safety, especially when it comes to electrical systems.
This is such a vital connection for any multidisciplinary designer. The core issue is the critical link between high equipment density and the risk of structural failure, particularly in life safety infrastructure. Electrical stability is a structural requirement.
Let's talk about fire command centers. The need for parallel circuit heat-induced resistance drift checks.
Okay, so in a densely packed mission-critical room like a command center, all of that equipment generates massive amounts of heat.
Right.
That heat dramatically increases the electrical resistance in the wiring and components. If that resistance drifts too far, even slightly, you risk signal deviation in crucial safety systems.
Like fire alarms, suppression controls, secure communications.
The system might misinterpret a signal, or its response time slows down. Catastrophic potential.
And in emergency operations centers, they have to evaluate thermal electrical cascade failure risks.
This is modeling a scenario where one localized thermal event, say an HVAC unit fails and causes a heat spike, leads to an electrical failure. The resulting resistance drift accelerates, and it threatens operational continuity across the entire critical system.
So if the internal heat load isn't managed structurally, if the cooling fails, it guarantees a cascading electrical outage.
An outage across essential communication and life safety systems, yeah.
The core takeaway here is just vital. Electrical stability is a life safety structural behavior. It's intimately linked to thermal performance, and it has to be designed with the same rigor as a column or a beam resisting gravity.
Absolutely. The building's ability to maintain safe electrical function under thermal stress is a prerequisite for life safety, period.
And finally, let's look at how the codes are starting to catch up to these dynamic concepts. Code insights on dynamic live loads, specifically IBC Structural Integrity Section 1609.9.
Concerning interactive snowdrift.
Right.
And this section really represents a maturation in how we view live loads. Snow is no longer treated as just some static, uniform blanket of white. It's a dynamic, redistributed load. This code forces designers of multi-level roofs to analyze that interactive snowdrift accumulation.
And the geometry of the roofs affects it hugely.
Massively. Wind shadow zones created by steps or parapets on multi-level roofs, they drastically increase the drift depth on the lower roofs, sometimes compounding the load by 3 or 4 times.
And that creates a highly unbalanced snow mass that's then subject to thaw-freeze cycles, which adds more density and weight irregularly.
Right. And the structure has to resist that asymmetry, specifically the roof diaphragm.
And for our listeners in governance or planning, can we quickly define a roof diaphragm?
Certainly. The roof diaphragm is essentially the horizontal structural plate, the decking and framing, that ties the walls and columns together. Its main job is to resist and distribute lateral forces like wind or seismic loads.
Okay.
In the case of snow, the diaphragm has to resist the rotational or torsional forces generated by that incredibly heavy, unbalanced snow mass. It has to prevent asymmetrical deflection or localized collapse during those thaw-freeze cycles. It requires drift-specific structural detailing that anticipates this highly non-uniform loading.
This entire deep dive, drawing from this KING-KAMBUF mentorship digest, it's been about understanding, predicting, and leveraging forces that constantly challenge a building's equilibrium.
That is the ultimate summary, yeah. All these forces, thermal, vibratory, hydrologic, atmospheric, they are actively seeking expression in the building. Elite design, especially for the audience we're targeting, is about either harnessing that expression architecturally,
Like we saw with the diurnal gravity theater.
or mitigating it effectively, like with the polar responsive coatings. It's a fundamental shift from static resistance to intelligent adaptation.
So what does this all mean?
Yeah.
We're moving into an era where buildings have to active participants in their environment. They have to be sensors and responders. They have to negotiate with the environment, not just endure it.
It elevates the role of the architect and engineer from just being stabilizers and aesthetic designers to being system strategists who are dealing with complex, nonlinear physics.
The future structure is constantly calculating risk and opportunity, making instantaneous decisions about its own performance and its own longevity.
That's the goal.
Which leaves us with a provocative closing thought for you, the listener. And this comes directly from the reflection posed in the source material itself. Reflect on the question, where does invisible environmental movement, thermal, vibratory, hydrologic, leave its fingerprints on architecture? And how can you design to reveal or mitigate it? Go explore the fingerprints on the buildings around you.